Hi there, Dr. Tishan here, and in this video we're going to evaluate a few limits using the rationalization technique. Let's review the limit concept and take a look at the notation here on the board. So recall that a limit, when you're finding a limit of a function, they're going to tell you where the x values are going from the left and the right, and as the x's approach a number, a value from the left and the right, our job is to tell them where the y values are going. So here's your notation. You take the limit as x approaches a value, a number from the left and the right of a function, okay? And so we're going to take a look at the function, the x values, and we want to see where the y values are going. So that's what the notation is. Now, evaluating limits, to evaluate limits, I have a flow chart over here that I use to summarize the concept of limits when you're evaluating analytically. According to the flow chart, if you have a limit problem and you want to solve a limit problem not using a table, not using a graph, well, then the first thing you want to do is you want to apply the substitution principle. The substitution principle says take your c value here, substitute it straight into your function. Substitute it in, and we want to see what comes out. All right, so what comes out? Well, let's see if you get a real number. If you have a real number, no zeros in the denominator real number, then that is your answer. That's what the limiting value is. That's where the y coordinates are going. If you plug in your c value to the function and you end up with a 0 in the denominator, it comes in two different forms, indeterminate form and undefined. If you get a 0 in the denominator, then we have more work to do. So this video, we're going to have 0 over 0 indeterminate form, and we're going to be using the conjugate on this flow chart, the rationalization technique. 0 over 0, with graphs with 0 over 0, essentially what that usually looks like, usually when you graph a function and you direct substitute the c value in and you have a 0 over 0, that implies that the c value, when x equals the c value of the function, is not defined there. However, as you approach from the left and from the right, you are approaching, the left and the right are going the same place. So there is a limit. We just have to do a lot of algebra to work it out and see what that limit might be. So let's take a look at example number 1 written on the board over here. Example number 1, we're taking the limit as the x's go to 4. We have radical x plus 5 minus 3 in the numerator, and we have x minus 4 in the denominator. So we want to go ahead and evaluate this limit. We don't have a graph, we don't have a table, so we're going to use algebraic techniques. So algebraic technique, what do we do first? Okay, so here's the flow chart. Limit problem, direct substitution principle. We are going to start by taking this number 4, substitute it into our function so we can see which branch we need to follow. So let's go ahead and do that. I'm going to work this out over here, just doing the arithmetic over here. Take the 4, the c value 4, and we substitute it in for x. In the numerator, that gives us radical 4 plus 5, and then subtract 3. In the denominator, substitute the 4 and gives us 4 minus 4. Simplify the numerator. So under the radical here, we have radical 9. 4 plus 5 is 9. We want to subtract 3. The denominator, we have 4 minus 4 still. One more step. Now the square root of 9 is 3. 3 minus 3 is 0. 4 minus 4 is 0. We have indeterminate form. We have indeterminate form. That means this function here is not defined at x equals 4. However, as the x's approach 4 from the left and from the right, there is going to be a limit. Okay, there is going to be a limit. This is not helping us find it yet, okay, but we know that it's approaching a value from the left and the right. We have to figure that out. How do we figure that out? Well, when you have indeterminate form with an algebraic expression, we want to see if there's any techniques we have to take the function and change the form of the function. We have a lot of techniques we can use. If you have an expression that's factorable, you can factor and cancel. I have another video on that if that helps. If it's a complex fraction, you can simplify the complex fraction, okay? In this case, if there are radicals involved in the numerator or in the denominator, you can rationalize, you can use the rationalization technique. You can rationalize the numerator, rationalize the denominator, utilizing the conjugate. If it's something that you can multiply out, if you have an algebraic expression, you can expand it, that works. And if all else fails, you always have those exceptions, always resort to a table, okay? So in this problem right here, we have to take this function and change its form. So how are we going to change the form of this function? Let's multiply numerator, denominator by the conjugate of this radical expression. What is the conjugate? It's going to be radical of x plus 5 plus 3, the conjugate, okay? And the denominator you have, you're going to multiply by the same thing, okay? So you're going to multiply, we don't want to change the form of the function, so whatever you multiply the numerator by, you need to multiply denominator by the same thing. If you reduced over here, this conjugate over the conjugate reduces to 1. It's like we're taking our expression and multiplying it by 1. So let's go ahead and multiply the numerators. We want to expand the numerators. So, and how will we expand the numerators? Let's do I'm going to erase over here. Let's do the algebra over here. We've already determined 0 over 0. All right. So we want to multiply the numerators together. So we have the limit as x approaches 4, and we want to expand the numerators. We want to multiply. So what do we have in the numerators? The numerators, we have the radical x plus 5 minus 3, and we have that multiplied by radical x plus 5 plus 3. This is what we have, and it's a binomial times a binomial, so you have to use the distribution process to multiply it out. So let's go ahead and start that distribution process. So you multiply these first terms together. Anytime you multiply a radical expression times a radical expression, you get the radical expression without the radical, right? Radical x plus 5 times radical x plus 5 is x plus 5, okay? All right, then let's distribute this term over to the end. So we're distributing here. So when you multiply this, you get positive 3 radical x plus 5. Now let's distribute the negative 3 term. To distribute the negative 3 term, multiply this way, you have minus 3 radical x plus 5s. And then finally, let's distribute the negative 3 to the last term. So you have to distribute both the terms in the first parentheses and both the terms in the second parentheses. You have a minus 9, negative 3 times positive 3. Now, do you notice that these middle terms drop out? You have 3 radical x plus 5s. You're taking away 3 radical x plus 5, so they cancel out. So what do we have here? We have the x plus 5. All right, these terms cancel out, minus 9. This is what we have when we square, okay? As a matter of fact, this turns out to be the difference of 2 squares, doesn't it? This turns out to be, if you look at, and this happens every single time you multiply conjugates together. Every time you multiply an expression times its conjugate, you will always have the square of the first term. Right, so take the x plus 5, the radical expression, square it, and then you'll always subtract the square of the second term. It's always going to leave you with the difference of 2 squares, and that's helpful to know so you don't have to go through all the steps of the algebra every single time. So when we multiply the numerator together, what did we get? We have x plus 5 minus 9. This is what we have, and it can be simplified, and we'll do that in the next step. What do we have in the denominator? Well, the denominator, you have x minus 4. We have this binomial factor, and we have this binomial expression, which is the conjugate, and so we want to write radical x plus 5 plus 3. Now, when we're evaluating limits, we want to expand the numerator. Yes, we want to expand the numerator, difference of 2 squares, but leave the denominator in factored form. Do not combine the denominators, okay? Because we're going to be able to cancel out common terms. We have to cancel out the 0 over 0 so we can solve this. So expand the numerator, do not expand the denominator. Now let's simplify. So we're taking the limit. We have the limit as x approaches 4. The numerator, you can combine 5 minus 9, so you have x minus 4. When you take positive 5 and a negative 9 and combine them, the denominator we have x minus 4 times conjugate expression, which is radical x plus 5 plus 3. So we're here, all right? Now, do you see where we're going with this? X minus 4 in the numerator, x minus 4 in the denominator. You have a common factor, they cancel. Okay, we can cancel these common factors, right? Now, does this always happen? Yes, this always happens, because if you direct substitute and you have 0 over 0, then you're going to have to simplify the function, get the 0 over 0 out of there. So if something's not factoring, go back and check your algebra, all right? So we have, let's see what we have next. So we're taking the limit. We're we simplify as x approaches 4, our numerator is 1 because we cancel out the x minus 4 factors. And our denominator, all we have left over now is the conjugate, radical x plus 5 plus 3. So we're here, all right? Now that we've taken our expression, completely simplified, all right, let's go back to how do we evaluate the limit? Now let's take the 4, substitute it in, and we can compute our limit. So take the 4 and substitute it in for x. When you take the number and substitute it in, you lose the limit expression. You don't have to write that anymore. So we have 1 in the numerator. And what about the denominator? We have radical 4 plus 5. And then plus 3 on the outside here. So when you simplify this, this is the square root of 9, right? Which is 3, and 3 plus 3 in the denominator is 1/6. So we found our limit. The answer for this problem is 1/6. This is the limit, this is the value that the y's are approaching. So if you were to look this up on a graphing calculator, graphing utility, you can do that. We're working these analytically though without a calculator. If you don't have a calculator, don't have a table, we're doing that way. So if you take the x's, as the x's approach 4 from the left and the right of this function right here, the y coordinates are going to 1/6. That's where they would be going. So that's what we're looking for here. So this function is not defined at x equals 4, but as the x's approach 4 from the left, from the right, it's where the y's are going. Okay, let's take a look at one more example just to reinforce the concept. I'll make it a little bit different, but let's take a look at one more example involving the conjugate. So let me erase this one. All right, we'll take some algebraic shortcuts on the expansion of the numerator when we're multiplying it out and so on. But all right, so we'll call this example number 2. In example number 2, let's take the limit as x approaches 3. Let's take the limit as x approaches 3. In the numerator, let's take 3 minus radical 2x plus 3. 3 minus radical quantity 2x plus 3. There's our numerator. And in our denominator, let's use x minus 3. So let's evaluate this, okay? We're not going to look at a graph. We're not going to make a table. All right, so let's go ahead and evaluate this. We're going to do this analytically. How do we start? Flowchart, review flowchart. All right, this is a little strategy to help you. How do you evaluate limits? Well, got a limit problem. Step 1, direct substitution. We take the c value, substitute it into the function. Off to the side, let's go ahead and take a look at where this is going to go. So we have 3 minus, under the radical, it's 2 times 3 plus 3. In the denominator, we have 3 minus 3. We took the x's in the function, we substituted 3. Let's compute to see what we're dealing with. So in the numerator, we have 3 minus radical 2 times 3, 6. 6 plus 3 is 9, isn't it? The denominator, we have 3 minus 3. So square root of 9 is 3. 3 minus 3 over 3 minus 3. We've got 0 over 0. 0 over 0. All right. So at x equals 3 on this function, there's a hole in the graph. That's this function. There's a hole in the graph. There's a point of discontinuity. All right, so the function's not defined at x equals 3. However, as the x's approach 3 from the left, from the right, the y's are going the same place. We got to figure out where. All right, so how do we do that? 0 over 0, and it's an algebraic expression. Can we factor and cancel? Not here. Nothing factorable. Numerator, denominator is not factorable. Is it a complex fraction that we can simplify? Not here, okay? Multiply by the conjugate. Do we have radicals involved? Yes, we do. Radicals with a binomial, so multiply by the conjugate. That's our strategy. What is the conjugate of this numerator? The conjugate of this numerator is going to be 3 plus, you got to change that operation sign, right? And then 2x plus 3 under the radical. And whenever we multiply the numerator by, keep everything balanced, we have to do the same thing with the denominator. We have to multiply numerator and denominator by the same thing. If you take conjugate and divide by the conjugate, you get 1. You're multiplying our function times 1, so we're not changing it, but we have to change the form of it so we can solve this. All right, let's multiply the numerator. Do you remember that technique to multiply it? This is it. Conjugate gives you an a minus b, a plus b format. So when you multiply it out, distributive property, it's going to give you difference of two squares. We're going to take the square of the first term, 9, minus square the second term. Now be careful here, because your second term, when you square the radical, you've got 2x plus 3, you've got two terms here, so we need grouping symbols. All right, so we need grouping symbols. When you square the radical, we need grouping symbols here because we're subtracting the second term. If the second term has more than one term in it, you have to distribute the minus the subtraction sign to each term. What about the denominator? Okay, so here's the numerator expanded. Square the first term, minus, okay, so you square the first term, okay, and then minus and square the second term. That middle term drops out, remember? Now, what about the denominator? Do not multiply the denominator out. We are going to keep the denominator in factored form. We're going to keep the denominator. Why do we keep the denominator in factored form? Because we're going to simplify and cancel common terms, okay? Now, this numerator, we've got the limit as x approaches 3. Let's simplify the numerator. We need to take this subtraction and distribute it. Okay, so distribute this subtraction sign. So you have 9 minus 2x and then minus 3. Okay, the denominator you have x minus 3, and we have 3 plus radical 2x plus 3. Okay, so there's your numerator, there's your denominator. Write that. Okay, combine like terms in the numerator. So you have the limit, x approaches 3. Right, in the numerator, so 9, so you have negative 2x, okay, and then 9 minus 3 is a positive 6, isn't it? Positive 6, okay, so you have the negative 2x, and then 9 minus 3 is 6. In your denominator, you have x minus 3, and we have 3 plus radical 2x plus 3. All right, can you see where this is going? All right, what can we do here? We can factor a negative 2 out of the numerator. Let's go ahead and do that. So we still have the limit x approaches 3. Now you have to keep writing the limit expression. You keep writing this down, proper notation. You don't lose that expression until you actually substitute the number, and we're not substituted in yet. So you can factor out the negative 2, factor out the negative 2 in the numerator. So take out the negative 2 from the first term, you have x. Subtract out the negative 2. So when you factor out the negative 2, you can have a negative 3 here, okay? And then your denominator, you have the x minus 3. And you have 3 plus, and then under the radical, 2x plus 3. All right. Now, we can go ahead and cancel the common factors. Do you see the x minus 3's? Let's cancel those, okay? So the x minus 3's cancel. All right. We're canceling the x minus 3 factors. All right, let me move this out of the way since I'm running out of space a little bit. And so now what do we have? Let's simplify here, okay? So what do we have now? We've got the limit as x approaches 3. In your numerator, the x minus 3's cancel, so you just have a negative 2 left in the numerator. What about our denominator? The x minus 3 factors cancel, so you have the conjugate expression left over in the denominator, which is 3 plus, and then under the radical 2x plus 3. So we completely simplified. We multiplied by the conjugate and simplified, factored and canceled. So let's take the 3 now and substitute it in. So take the 3 and substitute. I don't have to write this expression down because I'm making the substitution. Take the 3 and substitute it in. So in my numerator, I have negative 2. Denominator, substitute 3 in for x, so 3 plus, and then under the radical, I'll have 2 times 3, make that substitution plus 3, and we compute. Let's compute. So you have negative 2 in the numerator, and we have 3 plus radical 2 times 3 is 6, 6 plus 3 is 9 in the denominator, okay? So we end up with negative 2 in our numerator, 3 plus 3, so 6 in the denominator, negative 2 over 6 for your answer. If you feel to reduce, this is a fraction that can be reduced, so negative 1/3. So we do have an answer. we do have a limiting value for this function. We do. As the x's approach 3 from the left and the right, the y coordinates are going to -1/3. Anytime you're evaluating the limit analytically, don't have a table, you don't have a graph, and you're evaluating analytically. Anytime you're evaluating analytically, the first thing you want to do, direct substitution principle, you plug that c value in. If you have 0/0, if it's 0, if you end up with indeterminate form, that means from your left and the right, the graph, you're approaching an open circle. You're approaching the value, the c value is not defined there. So we have a lot of algebra to do. All right, so we do that. So evaluate the limit, you direct substitute the c value in to see what situation. If you have 0/0 in an algebraic problem, you just have a lot of algebra to do. Take your function that's given to you and change its form. Change its form somehow, okay? Techniques are listed up here on the screen. So, happy evaluating limits, and I hope this helps you, and I guess that's it. So thank you so much for watching, and I appreciate it. Bye-bye.